Hello, ladies and girls. No boys in this class, so there you are. Welcome this week. We're doing forces and Newton's laws. This is going to kind of bring together terms and definitions you've become more familiar with, things that are maybe common sense but do have a particular definition, such as speed versus velocity, uh, direction versus or distance versus displacement. So you don't want to forget the things we learned week 5 and 4, motion 1 and motion 2. We will refer to these terms without defining them any longer. So you may feel free to come back and look at them or refer to your notes if you have any confusion. So day 1 here, force and motion. What you can expect, I'm going to quickly take you 1 through 10, slides 1 through 10 for Monday. This is going to be a short review of what we've done and just kind of introduce the idea of force and how it pertains to motion. There is no motion without force. Then we're going to go a little history and specifics detour. You might have heard oftentimes in cartoons and movies, Newton's laws. Newton's laws. These are not attorneys. These are laws of physics. And so we'll go through the 3 laws. The one we'll spend the most time on is the first one, inertia. Then we'll spend, and that'll be Tuesday and Wednesday. And then we'll come back to this idea once we have an idea of what the first, second, and third laws of motion say about objects and their mass and what it takes to move them, the forces that it takes to move objects. We'll come back to all the various types of forces with the final lecture, which will probably be the longest one. And it's there'll be readings and videos as well. So this is a unit that could be, we could start with types of forces and then work our way back to Newton. We could start with Newton if we wanted and then work our way to forces. They all interrelate with each other. But I think this is a nice progression. We'll just start with this concept and this idea of force and motion. So to remind you of what you already know, the kinematics review, that's what you've been doing over the last 2 weeks. Once we get to forces, we call it dynamics. So kinematics is motion without force, just position. So the kinematics review, what is motion? Simply a change in the position of an object over time. If your arm was up by your face and now it is on the table, there was motion. There was a change in position. You didn't have to go anywhere, you just changed position. So strictly speaking, that's all that motion is. So how do you know something is in motion or has moved? Having looked at it, because it's all relative, you have to use a reference point. So don't forget that. Everything is moving in reference to something else, or sometimes seems like it is not moving from a particular reference point. So a stationary, not moving object, such as a tree, a street sign, or a line on the road, is standing still or is still in relation to the ground beneath it, because that's what it is attached to. Of course, universally speaking, it is moving, but it has no relative regard for motion. It doesn't move from our point of reference. So what causes an object to move? Why would a tree or a sign or a line on the road move? Well, it wouldn't. It would never move unless there was a force. It takes force to cause something to move. The 2 primary forces are push or pull. Very simple. Sounds scientific, right? I do believe, Dr. Belvedere, this car is moving. Why? Because we pushed it. Yes, scientific. But push and pull are 2 most common forces. They're why doors open. They're why our bodies move forward when our feet push us forward or our arms pull us forward. All motion is due to forces acting upon an object. There is no motion without a force. And the primary force is push or pull. So here you see the hand is applying a force against this car, which puts it in motion. So a total combination of these forces, opposite is negative, same direction is positive. Okay, so when you see diagrams, we're going to use a lot of diagrams to represent forces so that you can try to figure out what direction an object is moving according to the amount of force applied. But there's always more than just one force. There's usually multiple forces. So if you remember that a negative equals a force against a direction, and a positive is a force in the same direction acting on the object. So we can calculate or figure out its net force. If you know what your gross income is, if you get a check from a job you've worked, you don't usually get to take home all the money you earned. That's called your gross income. And then there's the net income, which is after the deductions, what you're left with, right? That's what you actually get to take. Well, net forces considers only the force that is applied that you can take home. There's other forces at play, but once you've made all the deductions of the forces in different directions, then you know your net force. So can more than one force act on an object at the same time? Absolutely. Gravity is pulling this guy down to the earth, but the earth is also supporting and pushing back up. This is called a normal force. And your legs are thrusting you forward, and that's only possible because of friction going in the opposite direction. All in all, the muscle in this body, if it overcomes that friction, is able to move forward. And gravity and normal force, that is here, number 1 and number 2, cancel out. Okay, so they kind of just keep you on the ground and still. But once you apply your forward push against the friction of the ground, you have forward progress. Congratulations. So balanced forces are what you see right here. No one's moving in this tug of war battle. These 3 people, even though they look like they have the upper edge with those 400 newtons on the left, these others that are on one foot at the moment are also pulling with 400 newtons. A newton is the measurement, the SI unit. So just like there's meters, liters, and grams, grams is weight, meters is distance, liters is volume, newtons is force. Congratulations, you just learned a new measurement, newtons, named after, of course, Isaac Newton. So a balanced force is one in which the net force will equal 0. When all forces are balanced out, no matter what that force is, if the net force is 0, then nothing moves. So do you think there will be any motion? Nope. These ladies are not putting any extra pull or push, and nothing is trying, maybe the wind, but the normal force pushing up from the earth because it's dense, more dense than they are, and the gravity pulling down on them is 50 newtons. They will stay right there in the sand. Likewise, these people go nowhere. So unbalanced forces. These are ones in which the net force is greater than 0. And all you got to do is look at the diagram. These are called free block diagrams. Here we have people, but we usually use circles, squares, and arrows. We'll ask you to identify those forces eventually. So, do you think there will be any motion in this diagram? These 2 are applying 25 newtons. These 3 are applying 40 newtons. So the arrow indicates the direction of the force. Okay, so all you got to do is take the difference. Clearly in the previous slide, there was 40 and 40. So what's the difference between 40 and 25? Well, whenever we say the difference, that means subtraction. So 40 minus 25 will leave you with 15. All right, so 15 newtons in what direction? Well, the arrow kind of tells you here it's going to be to the right. So the force produced by the blue team is greater than that of the purple team. So the net force is 15 newtons, and that would tip the rope directions to the right. All right. These skydivers, the air resistance will negate about 2 newtons of gravitational force. So you have gravity pulling them down, but you have all the wind beneath them pushing them back up. So that leaves then 48 newtons of a net force pushing skydivers to the ground. So even with the resistance, ultimately gravity will definitely win, and they will hit the ground with about 48 newtons of force. Smack. Unless they pull their parachute, and you increase the newtons of air resistance by increasing the surface area. Only an unbalanced force can change the motion of an object. If there is no unbalanced force, then it's balanced, and that's zero net force. That means zero movement. It would be just like no force at all. So you must have an unbalanced force, just like, say, your dog can cause you to move if he pulls with enough force, right? His force overcomes your force, and you're following that, and he's taking you for the walk instead of you taking him. So his force is greater than the force using to stay in place, overcame your muscles, overcame the friction, and so forth. So that's what we're going to be studying. You're going to have a reading, some questions, a video, and a lab today. And you're going to have a really good understanding of what force is. You can have a nice animation. Mr. Anderson from Bozeman Biology will give you some examples of force, and then you will play with some objects in your house to try to describe the different types of forces. I've only introduced two ways. Well, I have introduced friction. I've introduced gravity, but the two primary ones I introduced were pull and push. We'll return to all of these on Thursday. Tuesday and Wednesday, we'll continue to talk about Newton's laws with force and inertia. Okay. Oops, sorry, I had a couple more slides. So we're gonna, oh, you're familiar with these terms. All right, these are just review in terms of force, and you can read through these. These are self-explanatory. What would happen if an unbalanced force then acted on an object already in motion? Pause to think about that. That's what you'd call acceleration, right? If there was already movement and now you acted further, it's kind of like the merry-go-round. You have that spin and it's going, and they say faster. And so you grab it while it's spinning, you push it again, and they say faster. And as it comes around, you smack that bar again, and you're adding momentum. You're adding continued unbalance. As a matter of fact, more and more force. And so it's going to be going, of course, faster and faster. So if you would happen to add to, you're changing the speed or direction. That's what's going to happen with this unbalanced force. So riding a bicycle is another example. You run up behind them and you give them a push, or when you're trying to teach them how to ride a bike, and they're pedaling, and so they're already moving, but now you push behind them. So you're going to increase the speed. Your force adds to the existing force, causing him to speed up. So unbalanced forces connect in the same direction as well. So here's two people trying to move this chest. He's applying 15 newtons, the other going backwards can only apply 10 newtons, but together they're getting 25 newtons net force. So you would, in this case, because the arrows are going in the same direction, if you found a problem like this asking you what is the net force of movement and in what direction, okay, that'd be a common question. I would ask, what is the net force and what direction is it going? You would tell me net force of 25 newtons to the right, and you have to add that direction in there. If you don't tell me to the right, you're not giving me the net force. When two forces move in the same direction, the forces are combined. Now we're on the last slide. Unbalanced forces can act in opposite directions as well. Just as we saw in the push-pull example, the tug of war, here we have two dogs on a tugging on a rope. One dog pulls with a force of 20 newtons. The other is pulling with 25 newtons. Can you tell me what direction the rope is going to go? And what is the net force? 25, the difference between, and because the arrows are going in opposite directions, you're not going to add them together like you did here. If the arrows are in the same direction, you're adding them. But if they're going in opposite directions, you get the difference. So 25 minus 20 is 5 newtons difference. And it looks like 25 is on this side, the right. So you'd say 5 newtons to the right. That is the net force and the direction, 5 newtons to the right. So when you have opposing forces, the direction the object moves is in the same direction as the larger force. And that sounds like common sense, but it does confuse a few people when they see the diagrams. So just kind of review these slides, and this is it for day 1. Tomorrow we'll go over Newton's laws, or at least the first of Newton's laws. All right, get to the reading. Do watch the 5-minute video from Mr. Anderson. There's some great examples in there. And then do the mini lab in the comfort and joy of your own home.